Trick to calculate hybridization. In this lecture, I will teach you my personal trick to calculate hybridization of central atom in a very short period of time. I teach this trick only to special students to crack any exam question. So watch this lecture till the end and you will learn some advanced exam questions. Firstly, let me teach you my personal trick to calculate lone pair on central atom. Consider these elements of the periodic table. Now according to Roman numerals, this is the first group, second group, third group, fourth group, fifth group, seventh group and eighth group. We know that group 1, group 2, group 3 elements are metals. Their valency is their respective group numbers. For example, the valency of group 1 element is 1, the valency of group 2 elements is 2, and that of group 3 elements is 3. On the other hand, group 4, group 5, group 6, group 7, group 8 elements are non-metals. I subtract their group number from 8. For example, 8 minus 8 equals 0, 8 minus 7 equals 1, 8 minus 6 equals 2, 8 minus 5 equals 3, 8 minus 4 equals 4. So these are the valency of non-metals. Thus remember group number and valency of these elements. Now consider these molecules and find the lone pair on central atom. Well, to find lone pair, I use my personal formula, group number of central atom minus valency of atoms. For instance, in case of H2O, oxygen is the central atom minus there are 2 hydrogen atoms. We know that the group number of oxygen is 6 minus 2 and the valency of hydrogen is 1. I get 4 electrons. 4 electron means that there are 2 lone pairs of electrons present on central atom. In case of sulfur dioxide, we know that lone pair is equal to group number of central atom minus valency of surrounding atoms. Here, central atom is sulfur minus there are 2 atoms of oxygen. The group number of sulfur is 6 minus 2 and the valency of oxygen is 2. I get 2 electrons. 2 electrons mean that there is only 1 pair of electrons present on central atom. In case of NH3, we know that lone pair of electrons equals to group number of central atom minus valency of surrounding atoms. Here, the central atom is nitrogen minus there are 3 atoms of hydrogen. The group number of nitrogen is 5 minus 3 and the valency of hydrogen is 1. I get 2 electrons. 2 electrons mean that there is only 1 pair of electrons present on central atom. Thus using this formula, we can easily calculate the number of lone pairs of electrons on central atom. Now how can we calculate lone pair of electrons on central atom of ions? Well, consider these ions. We already know that the formula of lone pair is group number of central atom minus valency of surrounding atoms. Here, sulfur is central atom minus 4 oxygen atoms. We can see that there is negative 2 charge on this ion. This negative 2 means that this ion has gained 2 electrons. So I add these 2 electrons to central atom. I write sulfur plus 2 minus 4 oxygen atoms. Now the group number of sulfur is 6. I write 6 plus 2 minus 4 and the valency of oxygen is 2. After calculation, I get 0 electrons. So there is no lone pair of electrons present on central atom. In case of ammonium ion, I write nitrogen minus 4 hydrogen. This positive 1 means that this ion has lost 1 electron. So I subtract 1 electron from the central atom. I write nitrogen minus 1 minus 4 hydrogen. The group number of nitrogen is 5 and the valency of hydrogen is 1. I write 5 minus 1 minus 4 into 1. I get 0 electrons. So there is no lone pair of electrons present on central atom. Lastly, let me teach you one advanced level question. Calculate the lone pair of electrons on central atom. Here, xenon is central atom. So I write xenon minus oxygen minus 4 fluorine. The group number of xenon is 8 minus the valency of oxygen is 2 minus 4 and the valency of fluorine is 1. I get 2 electrons. So there is only one pair of electrons present on central atom. Thus using this trick, we can easily calculate lone pair of electrons on central atom. Secondly, if you have learned this trick, I congratulate you because you have already learned to find the hybridization of central atom. Now let me quickly teach you the concept of hybrid orbitals. If there are 2 orbitals, the hybrid orbitals is sp. If there are 3 orbitals, one is s and 2 are p hybrid orbitals. If there are 4 orbitals, one is s and 3 are p hybrid orbitals. If there are 5 orbitals, one is s, 3 are p and 1 is d hybrid orbitals. If there are 6 orbitals, one is s, 3 are p and 2 are d hybrid orbitals. Now what about their geometry or shapes? Well, we know that when the hybridization is sp, the geometry of the molecule is linear. Now we know that 3 means tri, 4 means tetra. In case of 5, I write tri which means 3 and I write bi which means 2. In case of 6, I write octa. Remember that octa means 8, but here we use it for 6. Now listen carefully. When hybridization is sp, the structure of molecule is linear. When hybridization is sp2, the structure of molecule is trigonal. When the hybridization is sp3, the structure of molecule is tetrahedral. When the hybridization is sp3d, the structure of molecule is trigonal bipyramidal. When the hybridization is sp3d2, the structure of molecule is octahedral. So note down this important list. Now let me teach you the super easy trick to find hybridization of central atom. Firstly, I write famous atoms along with their valency. Now consider these molecules. To find the hybridization of central atom, I use the formula lone pair plus number of atoms attached to the central atom or number of atoms surrounding the central atom. Firstly, I have to find the lone pair on central atom. In case of CH4, the central atom is carbon minus 4 hydrogen. We can see that the group number of carbon is 4 and the valency of hydrogen is 1. I get 0 electrons. So the lone pair of electron is 0 on central atom. What about its hybridization? Well, we know that hybridization equals lone pair plus number of atoms surrounding the central atom. Here, the lone pair is 0 plus 4 because 4 hydrogen atoms surround the central atom. I get 4 hybrid orbitals. This 4 means 1 is s and 3 are p hybrid orbitals. Thus the hybridization of carbon is sp3. What about its geometry? Well, this 4 stands for tetra or tetrahedral. So the geometry of CH4 is tetrahedral. In case of carbon dioxide, the central atom is carbon minus 2 oxygen. The group number of carbon is 4 and valency of oxygen is 2. I get 0 electrons. So the lone pair of electrons on carbon is 0. We know that hybridization is equal to lone pair plus number of atom surrounding the central atom. Here the lone pair is 0 plus 2 oxygen atoms. I get 2 hybrid orbitals. This 2 means 1 is s and 1 is p hybrid orbitals. Thus the hybridization of carbon is sp. We know that the geometry of sp is always linear. In case of NH3, the central atom is nitrogen minus 3 hydrogen. We know that the group number of nitrogen is 5 and the valency of hydrogen is 1. I get 2 electrons. So there is one lone pair of electrons present on central atom. We already know about hybridization. It is equal to lone pair plus number of atoms surrounding the central atom. Here there is only one lone pair and 3 atoms of hydrogen. I get 4 hybrid orbitals. This 4 means 1 is s and 3 are p hybrid orbitals. I get sp3 hybridization. Remember that this 4 stands for tetra or tetrahedral. So the geometry of this molecule is tetrahedral. Therefore, using this trick, we can easily calculate the hybridization of central atom. Now let me teach you some hard level question. Calculate the hybridization of xenon and the following molecules. Well, the central atom is xenon minus 4 fluorine. The group number of xenon is 8 and the valency of fluorine is 1. I get 4 electrons, or there are 2 lone pair of electrons present on central atom. Secondly, hybridization is equal to lone pair plus number of atom surrounding the central atom. I write 2 plus 4. I get 6 hybrid orbitals. This 6 means 1s, 3p and 2d hybrid orbitals. So the hybridization of xenon is sp3d2. We know that 6 stands for octa or octahedral. So the geometry of this molecule is octahedral. In case of this molecule, I write xenon minus oxygen minus 4 fluorine. I write 8 minus 2 minus 4 N2 1. I get 2 electrons or 1 pair of electrons. Secondly, hybridization is equal to lone pair of electrons plus number of atoms surrounding the central atom. I write 1 plus 5. I get 6 hybrid orbitals. This 6 means sp3d2. So the hybridization of xenon is sp3d2 and its geometry is tetrahedral. Therefore, using this trick, we can easily calculate the hybridization of central atom. Finally, let me teach you one exam question. Calculate the hybridization of nitrogen in the following ions. Well, I write nitrogen minus 3 oxygen. This negative 1 means that this ion has gained 1 electron. So I add 1 electron to the central atom. I write nitrogen plus minus 3 oxygen. We know that the group number of nitrogen is 5 and the valency of oxygen is 2. I get 0 electrons. So there is no lone pair present on central atom. Secondly, hybridization is equal to lone pair of electrons plus atoms surrounding the central atom. I write 0 plus 3. I get 3 hybrid orbitals. So 1 is s and 2 are p hybrid orbitals. Hence the hybridization of nitrogen is sp2. This 3 stands for tri or trigonal. So the structure or geometry of this molecule is trigonal. In case of this ion, I write nitrogen minus 2 oxygen. This ion has lost 1 electron. I write nitrogen minus 1 minus 2 oxygen, or 5 minus 1 minus 2 N2 2. I get 0 electrons or 0 lone pair of electrons. We know that hybridization is equal to lone pair of electrons plus atoms surrounding the central atom, or 0 plus 2 is equal to 2 hybrid orbitals. This 2 means 1 is s and 1 is p hybrid orbital. So hybridization of nitrogen is sp, and we know that for sp hybridization, the structure of molecule is always linear. In case of ammonium ion, I write nitrogen minus 4 hydrogen. It has lost one electron. I subtract one electron from the central atom. I write nitrogen minus 1 minus 4 hydrogen, or 5 minus 1 minus 4 and 2 1. I get 0 electrons or 0 lone pair of electrons. We know that hybridization is equal to lone pair plus number of atoms surrounding the central atom. Our hybridization is equal to 0 plus 4. I get 4 hybrid orbitals. This 4 means 1s and 3p hybrid orbitals. So the hybridization of nitrogen is sp3. We know that this 4 stands for tetra or tetrahedral. So the structure of this molecule is tetrahedral. Therefore, using this trick, we can easily calculate the hybridization of a central atom.